Vanakkam. Welcome to this video on biomechanics. We have been looking at measurement of kinematics or body segment kinematics in the human body using specific systems. We wanted to check how we can use IMUs to measure finger segment angles. So, we continue that discussion. So, in this video we will be continuing our discussion of these papers by my PhD students Prajwal, Anurag and Vignesh. For more details of this work and more of this kind of work, Google our lab web page, IIT Madras Neuromechanics. Google this and find our publications. Okay. So, in the last video we looked at how we can measure the kinematics of a single finger and represent that kinematics in real time or render that kinematics in real time using some modeling software like for example MATLAB Simulink or Unity. Right. Here we discuss how we can use similar principles to measure full hand kinematics. Okay. How many different sensors would you need and how many degrees of freedom would your model have? So, remember the distal phalanx only flexes and extends, the middle phalanx also the same. So, essentially the dip joint or the distal interphalangeal joint and the pip joint or the proximal interphalangeal joint are modeled as hinge joints or 1 degree of freedom joints. So, these 1 degree of freedom joints are all marked in red and yellow. All the sensors on the distal phalanx are modeled or marked here in red, okay, and all the middle phalanx sensors are marked in yellow. Okay. Actually, in the thumb you only have two phalanges, you have the proximal phalange and the distal phalange, right. So, these two segments, and then you have an extra special sensor which is the metacarpal sensor. We will come to that in just a little bit. Okay. So, the yellow on the thumb represents the proximal phalanx. Okay. These these 10 sensors are, that is the red sensors and the yellow sensors are all 1 degree of freedom, are required to measure only 1 degree of freedom. What are these? Flexion, extension, hyperextension. Well, hyperextension, does it happen? Well, it does not happen voluntarily, but I can apply an external force and make the distal phalanx to hyperextend a little bit like that. I can push. This happens when you are applying a force on an object, right. When the force exceeds a certain limit, your finger will start hyperextending, your distal phalanx will start hyperextending. So, flexion, extension, hyperextension is 1 degree of freedom. And then the metacarpophalangeal joint. Remember in the previous video I mentioned this, even in our anatomy class we have mentioned this. The metacarpophalangeal joint is a 2 degree of freedom joint, right. It can do this flexion, extension, and it can also do that abduction, adduction. So, abduction, adduction is the other degree of freedom that the proximal phalange or the proximal phalanx sensors are required to measure. So, the proximal phalanx sensors for the 4 digits index, middle and ring and little are 2 degrees of freedom sensors. There are 4 of them. Of course, the proximal phalanx in the thumb is a 1 degree of freedom, because there are only 2 segments in the thumb. Okay. And then a special sensor is present on the carpo-metacarpal joint or the carpo-metacarpal sensor, we call this. This is a 3 degree of freedom sensor because I can measure this, I can measure this and I can measure this, but there is a problem when I am placing my hand flat like this. There is naturally there is a variation in the angle between the where the carpo-metacarpal sensor is located and where the wrist or the reference sensor is located. You need to have an idea of that also. There is a normal here and there is a normal here, and if you want to measure the rotation, you need to have an idea of the angle between these two normals. Right. So, your wrist sensor is crucial in finding the measurement or finding the orientation of the carpo-metacarpal sensor. So, your carpo-metacarpal sensor is a special sensor. So, how many sensors do we have? Well, each finger has 3 sensors. So, 5 times 3 is 15 and 1 wrist sensor. You need 16 IMUs to measure your individual segmental orientations or angles. Among these, you have about 10 1 degree of freedom sensors, or 10 sensors measure only 1 degree of freedom, 4 sensors measure 2 degrees of freedom, 1 sensor is a reference sensor, and only 1 sensor measures 3 degrees of freedom. That 3 degree of freedom sensor is the carpo-metacarpal sensor of the thumb. Okay. So, these are the various sensors that are required to be placed on the fingers. Note that it takes time to instrument the hand with these sensors, because you need to place the sensor and you need to find a way to attach the sensors to the fingers. You can use surgical tape, some method. Double sided tape works, but in fast movements the sensor might slip. So, you might have to innovate there and find a combination between surgical tape and double sided tape. You might have to use both also, something that you learn only by experience. Our lab is relatively well experienced, regardless of whether we are equipped or not, we are well experienced in this art. So, we know how exactly to place the sensors. We have kind of innovated around the methods of placing sensors. So, the instrumentation time, if you are a newbie, it will take 45 minutes to 1 hour. Our lab students, my PhD scholars who work with me in our lab, they are able to instrument this in about 20 minutes, 15 to 20 minutes, because they have the expertise and they know what are the things to keep prepared for. So, they keep this the tapes ready, they keep the sensors ready. As soon as the participant comes, they just attach. Sometimes 2 students work in a coordinated fashion, synergy, to make this happen. Beyond this level, it is not possible to minimize the instrumentation time. Well, it may be possible, but at least we have not found this way, we are still working on it. Remember, human experimental time is a valuable thing. It is extremely hard to find human participants and get experimental time with them. So, you need to find a way to minimize the amount of time it takes for instrumentation and maximize the amount of experimental time. So, that is always a challenge as experimentalists, in particular a challenge in human experiments, because there are ethical constraints involved, right. Consider this, because there might be biological needs for the human participant. So, you need to finish your experiment before a need for some biological urge comes up, right. So, maybe they are thirsty, then you can give them water, but there are only so many things that you can do for them, right. So, there are challenges. So, we need to find a way to minimize the instrumentation time, and we are working on that. It is a continuous process, right. So, this is all fine. What is the particular method that we use? We use the Bosch BNO055 IMU chip and we built our own board. So, in our lab we have developed our own board around this Bosch BNO055 chip and developed the instrumentation around this chip. This is not an advertisement or an endorsement of Bosch BNO055. You can use any IMU you want, okay, and any microcontroller you want. I am only describing the method that is used in our lab, and I have to mention the specific method, all the details, and that includes the particular IMU, which is Bosch BNO055. What does it have? It has an acceleration sensor. Well, it is an IMU, so it will have an acceleration sensor. It has a gyroscope. What does a gyroscope do? Measures the angular velocity, right, and a magnetometer. Specific to Bosch BNO055, when compared with other IMUs, Bosch BNO055 has its own microcontroller. This is unique and this is very important. Because it has its own microcontroller, it can implement and run its own sensor fusion algorithm. It comes with hardware implementation of this sensor fusion algorithm, and it turns out Bosch says that these sensor fusion algorithms are optimized for measurement of human movements. This is unique because this is important, because your sensor fusion algorithm must take into account what is the application that is used. Here we are interested in measuring human movements, and Bosch says that this sensor fusion algorithm is optimized for human movements. We will have to take them, we will have to take this information for what it is worth. We do not know the details of this algorithm because it is implemented in hardware and it is probably proprietary, that Bosch will not want to share the details, so obviously. So, this is already implemented, you just have to set the parameters, you just have to give some details that you need to plug in into this microcontroller, and then it will run this algorithm and just give the output as the quaternion, that is it, right. It is a very small chip, that is important. Size is this, right, 3.8 mm by 5.2 mm by 1.1 mm. This is the size of the chip, not the board. This is the size of the chip. We need other components to measure. So, there will be a printed circuit board that will be built around this chip, that is going to consume a little bit more space. We will come to that in just a little bit. So, what does this Bosch BNO055 do? It measures acceleration, it provides gyroscopic data, that is angular velocities, provides magnetometer, and it has this unique, probably proprietary sensor fusion algorithm optimized for human movements, and it has its own microcontroller, right, and it can output linear acceleration, rotation, the direction of gravity, and quaternions, and it is relatively robust. So, these are the advantages, or these are the features of this particular IMU. There are other alternatives available. This is not an endorsement of Bosch BNO055 as I mentioned, but the challenge is that they may not have their own microcontrollers. So, you will need to implement the sensor fusion algorithm in your own microcontroller, and you need to develop the algorithm yourself, which you can do. That is likely to be more sensitive to the particular application if you know what you are doing. So, that requires some advanced skills in terms of coding and in terms of understanding of your own problem. So, there is no one size fits all solution. The solution that you want depends on how much you want, or how deeply or how badly, how desperately you want that particular solution, how much investment are you willing to make, not in terms of money, in terms of effort, in terms of time and other resources, right. So, there are challenges for everything. So, there might be limitations also, because if you want to measure from multiple segments simultaneously like we do in this case, 16 segments simultaneously, and if one particular microcontroller will have to perform sensor fusion for all the 16, that has to be a very powerful microcontroller. So, there are challenges, there are limitations and challenges in terms of what we can and cannot do using different this. So, there is no one size fits all solution. Here we just describe what we did, right. So, it is a relatively small chip that we built, around which we built a PCB. So, to start with, we just purchased some boards off the shelf that used BNO 055 at its core. So, we did not build it initially in the initial stage, we just purchased it off the shelf, because when you are testing these things, it is best that you test with something that is already available as opposed to reinventing the wheel. Once you know that something is working, then you can build for it. So, this is a test to decide whether you want to invest the time. So, we performed a static validation using off the shelf boards that are already available, and we 3D printed some frames that had known angles. So, these frames have known angles between two segments or two parts, and we placed, because we 3D printed them, we printed them such that we could firmly attach the two boards on these two segments of interest, such that, and we measured the relative orientation between these two segments in different conditions at different orientations of the same frame, and we had many different frames like this. We performed a validation in terms of whether the relative orientation between the two segments was captured relatively accurately. What we found was that only in some cases, only in some designs and in some of the angles, we had relatively large errors. These are not very large errors, about 3.5 degrees. Remember, this is static error, okay, this is a static error, and this was not there in all the cases. Here I am only discussing the highest possible errors. The highest errors we found in some designs and in some of the angles, right, not in all the cases. So, this is how we performed the static validation. To perform the dynamic validation, we made, again we 3D printed another system that could house these PCBs, these off the shelf PCBs, and our electromagnetic tracking sensors that are from polymers. These are polymers Liberty electromagnetic tracking sensors. Of course, these are sensitive to metals around them, and it uses a different principle. Remember, we discussed how this works in one of the previous videos. These are sensitive to metals, but the whole assembly is not made out of metal, right. This whole assembly is made out of probably out of PLA or ABS. This is 3D printed. So, we made it in such a way that we could rotate one of these joints at any speed that we want, at some reasonable speeds that we want, without breaking it, and we oriented two of these sensors in two different joints. So, we had electromagnetic tracking sensor and the IMU on the same platform in one segment. In the other segment, again we had the electromagnetic tracking sensor and the IMU. We assumed that the electromagnetic trackers, these polymers Liberty trackers, will give us the gold standard joint angles, right. So, that is what is considered as the basis for comparison, right. And we had a metronome that we followed, that we used to rotate the joint at various speeds. So, we rotated at various speeds starting 30 degree per second to 240 degrees per second. And what did we find? Well, what is plotted here is the angles that we measured using both Bosch BNO 055 and the electromagnetic tracker. Both of these are plotted, and what we find is that at relatively slow speeds, right, there is very little or no error, very small amounts of error, right, or at least it is not visible in the, you are not able to identify it using your eyes, but you can see if you look closely there is a small amount of error, especially at times when there is a directional change. Suddenly when there is an acceleration, suddenly when you are changing directions, it seems like there is a small error that happens at relatively slow speeds. What happens at the highest speed is what caught our attention. That is presented in this frame. What happens at the highest speed is, once you start moving at this highest speed, the Bosch BNO 055 starts showing some error, and it turns out that this error appears to propagate from one cycle to the other. In other words, as the number of cycles increases, the error appears to become bigger and bigger and bigger. Remember, this is a cyclical task we just did, tick 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 tick. So, it is a cyclical task. If you do a cyclical task at a very high speed, you are going to have a relatively large error towards the later cycles, especially towards the later cycles in your Bosch BNO 055 measurement. This is what we found. Then we asked the question, does it really matter how often are you going to perform the same cyclical task at very high speeds? How likely it is in human movements? We thought, and we still believe, that that is not a very likely scenario. So, this is not something that we need to worry about, because here we are interested in measuring relative orientation between segments in everyday life, and in everyday life you rarely perform these high speed movements for very long time in cyclical fashion. That is very unlikely, something that we learned. But something to keep in mind, that there are these errors that happen with Bosch BNO 055, where the error keeps on increasing with later cycles. As the number of cycles increases, the error appears to propagate. That is something that we can keep in mind. So, this is what we found, and the RMS error for most cases was below 4 degrees. This is presented in one of the two papers that that we just discussed. The details are all available in the papers. Here I am not providing the details, I am just introducing this. Okay. And how did we measure this? We had 16 sensors. Remember, what are these 16 sensors? 3 sensors for each finger, and 5 fingers is 15, and the wrist sensor. Of course, not all of them are the same. The 15th sensor, for example, is the carpo-metacarpal sensor, which is a 3 degree of freedom sensor, but these are 16 sensors. And because each sensor has only 2 addressable spaces or 2 addressable units, we need to find a way to measure multiple data from these many sensors. So, we used an I2C multiplexer, and because each sensor takes about 2 milliseconds to provide data. Why does it take 2 milliseconds? Because it collects the data and then very quickly performs the sensor fusion and then outputs the quaternion. It needs that processing time, 2 milliseconds it takes. So, when requested, the IMU will provide data in 2 milliseconds, and because we are using multiplexing, the multiplexer will measure data sequentially one after the other, and there are 16 of these. To measure one set of angles or to measure one set of quaternions from all the 16 sensors, it takes 16 times 2 32 milliseconds. It takes about 32 milliseconds to have one full set of quaternions from all the fingers, from all the segments. But that means if I am, what is the maximum speed at which I can measure? Well, that is about 30 hertz, right? 30 hertz. If the moments are below 15 hertz, then you will not have the aliasing problem. Read about this, okay? Read about what is the aliasing problem and what is the Nyquist criterion. I am just mentioning this for you to check, okay? Nyquist criterion, aliasing problem. If the movements are going to happen at frequencies below 15 hertz, you won't have problem with measuring at 30 hertz. But you know, I am a tough taskmaster. I told the students 30 hertz not acceptable, 100 hertz, minimum 100 hertz. I am a tough taskmaster and my students are also brilliant. They figured out a way to measure this at 100 hertz. We provide the details of how we did this in the paper, but very briefly I will describe what we did. What we did was, we used one microcontroller for one finger measurement, okay. Like this, we used 4 microcontrollers for 4 fingers and a 5th microcontroller that measures from the 5th finger as well as gives commands to the other 4 microcontrollers. This of course increases the cost of the system, but it also increases the maximum frequency at which I can measure. You can't have the cake and eat it too. I cannot say I want to minimize the cost, at the same time I want 500 hertz measurement. Sorry, that is not possible. You just cough up the money. This is how it works. You just give the money. So I suggested at that time, first let us crack the technology problem, then we will crack the cost problem. You need to decide which is the problem that you want to crack. For me, this limitation of 30 hertz was unacceptable. 30 hertz unacceptable. It's fine. I'm happy. I'm glad that we are able to measure at 30 hertz, but I want 100 hertz. That's it. No compromise. See, when you put some brilliant people in a situation where there is no compromise, then they will figure out a way. Of course, I said that there is no constraint on money. There is no constraint on cost. You need to give them some leeway, otherwise how will they solve problems? Otherwise it is impossible to solve problems. You can't put checks on all the dimensions. I said there's money, instrumentation, hardware is not a problem, but I want 100 hertz. You need to start there, and then you need to reduce the amount of hardware, try to minimize it, and then reduce the cost. There are other ways of doing this, but technological requirement or a technical requirement like 100 hertz is something that I cannot compromise on. Suppose there are components of movements that is about say 20 hertz, and I know for a fact from previous experience, I have worked in this field for a long time, I know from my previous experience there are movements that have components at around 20 to 25 hertz. Some movements have, not all movements, these are very fast movements of course. There are some hand finger movements that happen just about 20 hertz. These movements will not be captured using a 30 hertz system because of the aliasing problem. Check what this problem is, because that is going slightly outside our discussion, but do read up on this, right. So there are constraints, the students came up with this solution whereby we use a master and slave arrangement where one microcontroller gives commands to 4 microcontrollers that acts as the slaves, and those 4 measure as soon as they receive a command from the master and measure data from one finger at a time, right. So the exact solution and the details are available in the paper, but briefly this is what we did. There is an increase in cost because 5 microcontrollers, these teensy microcontrollers that we used are expensive. For 5 microcontrollers means 5x the cost. You can't have the cake and eat it too. You need to decide what you want. So, here we focus on cracking the technical problem. In future, we are still working on improving this. In future, we are very confident that we will be able to develop a system that will be able to accomplish exactly this, but at a fraction of the cost. But that takes time. So, you need to decide which problem you want to crack first. Always, this is my suggestion. I am not saying this is the best suggestion. Always crack the technical problem first, then crack the affordability problem. These are two independent dimensions. You can't crack both simultaneously. First crack the technical problem, so you have a grasp of the problem itself. Then the affordability cost problem can be addressed in many ways. There are many ways of addressing the cost problem. Scale, for example, is one solution, but not just that, there are other ways of solving this. Okay. So, that is what we did, and look at the amount of cabling that we had. This picture presents the cables that we used in the initial prototype that we had. The amount of cabling and the amount of surgical tape that we used, practically people, can they even move normally? That is the question. That is how much surgical tape and cabling that we had, but that is not the point. The point is, are you able to measure? Here we are providing proof for a principle. This is proof of concept. We are showing that this is possible first, and then we show that we then improve on this design to further make it more sleek, more unique, more special and smaller, etc. Of course, validation of this using Polymer's Liberty or the electromagnetic tracker and the Bosch B&O simultaneously is not possible, because it is nearly impossible, in our opinion impossible, to simultaneously mount the Polymer's Liberty sensor and the IMU sensor on the finger segment. We do have the small Polymer's Liberty sensor in our lab. We have the 1.8 mm dia Polymer's Liberty sensor. Even that, it is not so easy to instrument. I am still working on that. I will still try to see if it is possible to do that. We have to innovate. We have to innovate this. So, here we made these measurements at 2 different times, and we show how these are rendered or represented by the Bosch B&O 055 system with 16 sensors and polymers, right. And we found relatively good accuracy with the Bosch B&O 055. Remember, the Polymer's Liberty system is extremely expensive, it is very expensive, and also it is somewhat delicate, it is fragile. You need to be very cautious how you use it, it is very expensive, right. So, but the IMU system is relatively less expensive, it is much less expensive when compared with the Polymer's Liberty system, and it is giving you comparable accuracy. In fact, in some cases, for example, this one, right, the rendering in Bosch B&O 055 was much better when compared with Polymer's Liberty. These are some examples that we show, right. But the point is that we are able to relatively accurately capture the finger segmental joint angles using the Bosch B&O 055 IMU system. Okay. So, how did we build this? What is the final product or miniaturized version look like? So, each board, it has a dimension of 1.3 centimeters by 1 centimeter, right, and that is what is placed in one finger segment, okay. And each of this sensor is mounted on a 3D printed mount, which is then attached to the segment. Now, there are many problems. I know that serious followers of biomechanics will question, hey, now there are many problems. There is artifact, that is relative movement between the skin and the mount, and there may be relative movement between the mount and the sensor. Yes, we have minimized the amount of movement between the mount and the sensor already. The mount is necessary because it helps us to properly attach the sensor block itself to the segment. Otherwise, you cannot directly attach a PCB because it will make the whole system fragile and extremely sensitive. So, we need a mounting for that. And then we have these 4 microcontrollers. These are teensy 4.0 microcontrollers, and then we have the 5th microcontroller here, that is the master, that is also a teensy 4.0 microcontroller, and we had a Wi-Fi module that sends data wirelessly to a computer, and it operates out of a battery or a power bank. We just got a regular power bank that is available for phones just for testing purpose, and we used, as opposed to the cabling in the previous slides, we used FFC cables that that make the whole system a lot more manageable and a lot more sleek. So, this is what we did. The size was much more manageable, right, so that we can actually mount it on each individual segment. So, this is the arrangement. So, you have these 4 slave microcontrollers sending commands to each of the fingers. This one is sending command to the this finger is receiving command directly from the master, and it is measuring 4 sensor data simultaneously. It is measuring 4 sensor data simultaneously. So, that is the limit at which I can measure, right. 4 times 2 milliseconds is 8 milliseconds, and that means that in 1 second I can measure 1000 by 8 times. Maximum speed at which I can measure is, the maximum speed is 125 hertz. Okay. Of course, we are measuring only at 100 hertz, but just giving a pointer as to what is the bottleneck. The bottleneck is the one that is measuring with 4 sensors. Why do you need this? Why do you need 4 sensors? Well, because I have 3 sets of sensors in each finger, but I also have a reference sensor, that is the 4th sensor in one case. So, I have 5 sets of 3 sensors, and then I have 1 extra reference sensor. Someone has to measure that. That is measured by this master. Okay. So, this is the cable connection diagrams that provides all the little details. They are all present in our paper. I am requesting you to please read these details in our original publications. Okay. Here what is shown is a rendering of measurement made using this system. Real time rendering of various postures of the hand. Wi-Fi, 100 hertz, real time, maximum dynamic error is about 4 degrees, maximum error is about 4 degrees. And this is comparison between our hand kinematics measurement system and the electromagnetic trackers that we got. Of course, not measured at the same time, at 2 different times. So, same task is performed by these 2 systems at 2 different times, and we are just playing these animations one after the other. So, We are just playing this animation side by side. I mean, right. And then we used this system to try and visualize how different postures are performed by the human hand, by making people perform different types of postures. First we started with Bharatanatyam postures, because in Bharatanatyam abhinayas or finger postures are used to communicate specific feelings or emotions or whatever that is. I am not an expert in that field. What is Bharatanatyam? Bharatanatyam is an Indian aesthetic dance form. So, it is an Indian dance form. So, these are aesthetic movements. Not all these postures are easy to perform. Some of them are hard, some of them are relatively easy to perform. The point is that we captured about 8-10 Bharatanatyam postures. We also used some American Sign Language postures, some numbers, some letters, and we had some physical objects that was made out of plastic. Some of them used pinch grip, some of them used cylindrical grip, some of them used tripod grasp, some of them used prismatic precision grasp, different types of grasps. Okay. Using all these, we made measurement using our IMU based system, and we rendered these using software, and we compared this rendering between our measurement system, which we call as a human hand kinematic measurement system, HKMS, and the electromagnetic tracking system, of course done at 2 different times, and we render this and we compare the rendering between the two, and we did not find very different postures rendered by our system. The accuracy is almost comparable. So, with this innovation we have almost achieved about 30-40 fold reduction in cost. Of course, accuracy in research grade is compromised. Our accuracy is about 4 degrees, or the maximum error is about 4 degrees. So, it is not comparable to the polymers errors, I understand that, but for most purposes, work on human motor control for example, this kind of accuracy will be more or less acceptable. So, something to keep in mind. We also compared, just for safety purpose, just for as a check, as a post check, we also compared whether the range of joint angles that you get in a set of all movements performed by a set of all participants are comparable between the electromagnetic system and the our IMU based system, and we found that they are almost comparable. Right. There were some differences in some cases, and those differences are all highlighted here. In some cases the difference was about 14 degrees and 13 degrees, and in some cases the HKMS had a higher range, in some cases the electromagnetic tracking system or the EMTS had a higher range. There were some differences, but mostly they were comparable, the ranges were comparable. The purpose of this is to show that it is not very different. Our system is not measuring something that is completely different physically, right? It's measuring the same thing at approximately acceptable accuracy, at approximately comparable levels of accuracy. So, it is providing more confidence in your measurements. Right. Here is some rendering of the various tasks that are performed. Right. This is opening and closing of a cylinder. These are postures that are performed. Remember, this whole measurement is wireless 100 hertz, and because we developed it for one hand, we can instrument the one more system on the other hand and study two hand tasks. Studying two hand tasks using optical system or a polymer's liberty based system is going to be extraordinarily expensive, very expensive, even in developed countries. In any lab, well funded lab, studying two hand kinematics is a great challenge. Right. And then we show rendering of movements that are performed with one hand and both hands in virtual environment. So, we see how learning is performed, is what student Anurag is doing with this free advertisement for Oculus. Inadvertent, not meant to be an advertisement. This. And then rendering of various postures. For various postures, how is the hand responding? This whole thing is going to cost about the cost of building. It's about say $2,000 or 1.5 lakh rupees, a little more than that maybe. The cost at which we sell may be different depending on this. The cost of this is about couple of thousands of dollars. Very inexpensive system. Wireless 100 hertz measurement and having an accuracy of less than 4 degrees. You can't get better than this. This is definitely free advertisement for our own lab product. Alright, something that you notice with these renderings is these kind of finger touches are relatively hard to capture. Some of these finger touches are not captured, especially this one, where the little fingertip and the thumb are touching, because this palm arch is relatively hard to model. And so, I am not saying this is a perfect system, there are challenges, but these challenges are there in all systems. These challenges, palm arch is hard to model even in other systems, are hard to capture even in other systems. So, capturing this little fingertip to the thumb tip is not a trivial task. So, we are also not able to capture this. So, we are honest about that, we accept what we can and we cannot do. So, with this we come to the end of this video. In this video we looked at a couple of papers that is published from our lab, where we used an electromagnetic tracking system to validate the performance of our in-house developed hand kinematic measurement system using IMUs, and we showed that we are having acceptable accuracy levels. The errors are less than 4 degrees and relatively high speed measurements captured wirelessly. And we also showed how we developed the printed circuit board for this system and how we measured the data using microcontroller and how we rendered it, how we communicated this, how we developed a communication system wireless for this system. With this we come to the end of this video. Thank you very much for your attention.